none of it really matters too much to just show this. But the guy made a weld. That's glycerin that he just dropped the weld in. And you come back a few minutes later and you can see the hydrogen bubbling out of the weld. So this is sort of like my Sprite, okay, where you saw the bubbles, except this is in glycerin, so it retains the bubbles. They don't pop to the surface within a fraction of a second. And so you can see they're showing different types of electrodes. This is a E7018 perhaps, okay, electrode. They have XX, they're not telling you the strength level. There's 80 18s and 90 18s and 110 18s for different yield stresses. Okay. But you can see the hydrogen bubbling out, just like the CO2 coming out of the Sprite. Okay. The whole thing is probably, well, I wouldn't have sent the link to you if I didn't think it was worth looking at. But anybody have any questions? It really does bubble out. And it comes out very quickly, and if you come back a couple hours later, there will still be a few bubbles there. Okay. Because the glycerin traps them. Any questions on that? If not, I'm going to go back to my regular mode, which is this thing. I think I explained last term to those of you that were in class that the reason I use this is because I have no idea what I'm going to talk about today. It depends on what questions you ask. So we've talked about faults in fusion welds and how hydrogen can cause cracking, and you get what are called, blow it up a little bit, underbead cracks, toe cracks. These are underbead cracks over here. This is a toe crack. Usually the toe crack's right at the toe of the weld. Okay, root cracks coming up from the bottom wherever you have a change in section, you have a stress concentration. Remember, the higher the stress, the higher the hardness, the higher the hydrogen level, the greater the propensity. And we use Venn diagrams to show this, okay? Now, I also showed you this before. And this is one of the only places you'll actually, this comes out of the Welding Institute book on welding steels without hydrogen cracking. It talks about the weld hydrogen level in milliliters per 100 grams, which is almost the same as parts per million, within 2 or 3%, I think. It works out. And this is the potential hydrogen. Potentially, these stick electrodes, these things that we've passed around before, can give you, well, they'll have anywhere from 0.2 to 1% moisture or more, and they can give you very high levels of hydrogen, potentially in the weld. 100 ppm or more, but in fact much of it goes away very quickly in the welding process, and you may end up with only 4 ppm. And in fact, we're going to see that what's called extra low hydrogen welding electrodes tend to be, they will guarantee that when you first take them out of their hermetically sealed can, they'll be 4 ppm or less. Cellulosic electrodes or basic electrodes can give you 30 ppm hydrogen in the weld, okay? And what I've done here is, if you actually deconvolute a lot of the data in the literature, you can come up with something like this. If I have a steel of 70 KSI tensile strength, and that's mild steel, okay? That's what your little red radio flyer wagon that you pulled around as a child, or your typical cheap bicycle, is made out of 70 KSI steel. You can tolerate 30 ppm, and you gotta really use no hydrogen control at all to get enough hydrogen in there to crack it. And you have to have a high enough stress. Well, if I'm welding on sheet metal like the radio flyer wagon or the tubes for the bicycle, it's pretty hard to get hydrogen cracking. You don't have enough restraint. You gotta have something that's big and thick. Something like a piece of submarine steel that I passed around before, and now I will pass around this. This was a piece of 10-inch forging, cast forging. It's a little heavy. I'll pass it around with a rag. The edges are not that sharp, but there's probably 400 passes in there. And I had put that up on the screen at the last class, I think. That's got a lot of residual stresses, because every one of those passes shrinks. about 2.5% as it solidifies. And then it shrinks some more as it cools down. And that, when it's restrained, because the rest of this thing weighed 60 tons, there's nowhere for it to shrink to. So all that goes into strain. Some of it's yielding, but you get yield level residual stresses. The yield level residual stresses are the highest stresses you're going to get. In some cases, in something like that, you can actually get higher than yield because you get triaxial stresses, but we won't get into that, okay? But your stress can get as high in thick sections as whatever the tensile strength of the material is. So since your stress circle can get bigger and bigger as you go down in strength or up in strength, you can tolerate less and less hydrogen, because as this circle gets bigger, this one better get smaller in order to avoid that, right? Or you need to control your hardness. It means you start with a steel with a low carbon, because remember, hardness is proportional to carbon, right? So we've spent a lot more time than I thought I might talking about the basics of steel metallurgy to get to the point where we can now start talking about welding procedures. But before I get there, I want to put this up. It turns out we just live in this perfect world at 20 degrees centigrade. And if I look at the tendency to form a crack, which is notch tensile strength, the lower the notch tensile strength, the easier it is to form a crack. And I look at a hydrogen-free specimen, it will have a fairly high strength. If I look at a hydrogen and brittle specimen, I could have up to 75% reduction in strength because of the hydrogen. So a steel that might have 100 KSI strength might crack at 25 KSI. Okay? However, if I go up in temperature, it takes more and more stress. Why? Because as I go up in temperature, that hydrogen comes out faster. It doesn't have time to migrate to that crack tip. It diffuses out before it does its damage. Right. The question is, and I have realized by watching some of the tapes, because I've got the mic on, people can't hear your question. So the question is, how do you know what temperature you go to? Well, people have learned that about an hour at 375 or 3 hours or 4 hours, depending, it turns out the higher the strength of the steel, the lower you have to get in hydrogen, and so that means the longer the time. And the experience is, if you're at this 200 KSI, 700 mega, or 1.4 gigapascal strength level, you're going to need 23 hours, a full day at 375. Okay? Why is that? Well, there are hydrogen traps in the steel. The hydrogen, not only will it go to crack tips, it will go to inclusions, little dirt particles in the steel. And in fact, there's a guy out at Colorado School of Mines who was elected to the National Academy because he showed that if you have slightly dirty steel, it's better than if you have very clean steel in terms of hydrogen embrittlement. Okay? You want to have some inclusions to trap the hydrogen so it doesn't go all to the bad places. You have hydrogen traps. And people have studied what temperature the hydrogen is released from the traps. And so typically 375 Fahrenheit is the number that people use. There's still hydrogen comes out above that. But in general, it's a time temperature diffusion thing. What's the concentration? Up here in these types of steels, 1 hour at 375 is plenty. In these steels, you might need a day at 375 to get to these levels, at the higher strength levels. There's not a fixed number. But I'm going to show you something that allows you to calculate all this. Well, the question is, does this 375 cause warping? No. Steel, to start relieve residual stresses or introduce warping in steel, you've got to be above 900 degrees Fahrenheit. Typically, we stress relieve steels in the 1100 to 1200 degree Fahrenheit range. And that's where you're actually starting to see the steel creep like silly putty, if you will. You can't see it creep like silly putty, but it's creeping enough to relieve the strains that are locked in. We talk about residual stresses, they're really locked in strains. Okay, and if I have a piece of steel, let me take this and say this is a piece of steel, and I machine away the top layer, if it's got residual stresses, it will warp because I took away the residual stresses here. It might warp down, it might warp up. But in fact, that type of distortion, if I take a heat-treated part, whether it's steel or aluminum that's been heat-treated, I start machining it, and it walks on me. It can move 10, 15 thousandths. I'm trying to do precision machining on a heat-treated metal part. I got problems, okay? It will move on me, and so you have to stress relieve the part before you're going to do some machining. In fact, a number of years ago, it was a big problem in the lithography business for making computer chips. They needed to machine things within tolerances of like 5 microns. Okay, that's 0.2 mils or 0.0002 inches. Okay, 5 microns. You can't do that. Even if you stress relieve the steel or the aluminum, it will still move that much if you machine off a quarter of the thickness out of a 1-inch plate. You can machine it and you come back and you measure it and it's moved. So you have to machine it again. Okay? And then it moves a little bit more. Okay? It does sort of start, tapering off. But you have to be careful. You try to grind something flat and you start getting very precise. In fact, if we want to talk precision, does anybody know what the typical manufacturing tolerances are for machining steel or whatever in parts per million? So if I have something 1 inch long and I want to machine it, I got a big bar of steel and I want to turn it to 1 inch diameter. What's the typical tolerance that I could expect a machinist to come back with without a novice machinist? Plus or minus 1 thou. It might be, for you and me, it might be plus or minus 5 thou. But a guy who's a machinist and this is his trade, he ought to be able to hold 1,000ths. Okay? Now a guy who's been a machinist for 20 years, he ought to be able to hold 2/10. Okay? 5 microns. Or out of 1 inch. Okay? Or maybe he can hold 1/10. But boy, he's measuring things. He's making sure, that there's no stress on it when he clamps it up and everything else. That's per inch. If I got something 10 inches long, the tolerance is not 5 microns, it's 50 microns, which is 2/1000ths of an inch. So telling you that, what is the most precise manufacturing in the world? In parts per million or parts per thousand of what tolerance you can hold. Well, first of all, you start getting down to 10 to the minus 5, you're now getting into thermal expansion. When you're removing that material or adding that material, you got to know what temperature is, because the typical coefficient of thermal expansion is 10 to the minus 5 per degree C. 1 degree C change in temperature, and you're going to have 10 parts per million of movement. Okay? So when I worked on some helicopter bearings on some of the world's largest helicopters. 42-inch bearing, half-inch raceway, what were they, quarter-inch balls or something like that. And it was 42 inches wide. It was supposed to be 42 inches plus or minus 5 thousandths. Well, that's like 1 part in 10,000. So what do? They put the mic, which is just a big bar mic, to measure this 42 inches. They put it right on the bed that was filled with oil while they were machining, so it'd be at this exact same temperature. Because the measuring tool has to be at the same temperature as the part you're measuring, or you're going to get an inaccurate measurement, right? So they bathe the measuring tool in the same, cooling bath and lubricating bath they did the other stuff. So again, I'm going to ask you, what is the world's most precise manufacturing in parts per thousand or parts per million of accuracy tolerance? Well, we can do either one. Okay, the I'll tell you, the secret is it's the biggest part and it's the smallest part. Okay? If you go to shipbuilding, you've got to hold a 1/4 of an inch over 100 yards. Start figuring that out. It's about 1 part in 20 or 30,000. Okay? It's much finer than some guy trying to mill or machine a bar to 1 inch plus or minus 10 thousandths of an inch. Okay? Or 10 thousandths of an inch. 1/10,000th of an inch. Okay? It's much better than 10 minus 4. Or maybe it's, I can't remember. You can calculate it. 1/4 inch over, because you got to put the steel plates together, and they can't be put together like that. They have to go together like that, right? The other one is, it turns out, it used to be 10 years ago, shipbuilding was by far the most precise. Turns out, semiconductors, when I'm getting down to 0.14 microns, or no, 0.14, 14 nanometers over a centimeter, you start figuring that out, and you're getting to just a little bit better than shipbuilding now. You have to go on the extremes, very small or very large, to get the most precise tolerance. In a shipyard, they have to worry about when the sun comes out from behind the clouds, because the heat on that side of the ship will cause the whole ship to bow when they're building the ship, and the distortion will. Yes. No, it's what tolerance and dimension can you hold? If your spec is 1 inch exactly, what's your tolerance on that? You ought to be able to give it to a novice machinist, and he ought to be able to hold 1/1000th of an inch. So it's 1.001 or 0.999 to 1.001. That's 1 part per thousand. Okay. If he's holding 1/10 of a thousandth, 0.0001 plus or minus, that's 1 part in 10,000. Okay. But you start thinking about 1/4 of an inch over 100 yards, you can calculate what parts per thousand is, and it's going to be, I don't remember, 1 in 20,000. It's more than 1 in 20,000. It's 1 in 30,000 or 1 in 100,000. If you start getting down to nanometers of a silicon chip, those dimensions, over the length of the chip, which is about a centimeter, you're also getting into the one part in tens of thousands or hundreds of thousands. Okay. What, on the chips? You don't etch the chips. Okay, we got chips on one end, we got ships on the other end, right? Okay, the chips, they use photolithography, although now they're using high ultraviolet lithography, because you get into the problem of the wavelength of light. Okay, which, I mean, these dimensions are smaller than the wavelength of just visible light, so they're using ultraviolet. They've talked about using electron beam lithography and things. Some of them, I believe, they actually pattern one part of the chip and then they match it to another and match it to another, because over a centimeter you can't hold that type of tolerance. Okay, but there's a lot of things, and I'm not an expert in that area, but at one time this was supposed to be a $20 billion problem for the semiconductor industry about 10 or 15 years ago. Your dad worked on some of that. Yeah. So anyway. So the point here, getting back to welding, unless there's other questions, is you can get rid of the hydrogen at higher temperatures than room temperature. You can lock it so it doesn't diffuse around to do its damage at lower temperatures. The absolutely worst temperature is right around room temperature. Lucky us. Okay, that's where we live, and that's where hydrogen is the worst. This is just a schematic. I do have a plot that actually gives you hard data. This is not from welding. It's from hydrogen sulfide stress corrosion cracking. Yesterday, one of you asked the question about what's stress corrosion cracking, and I got up here and said, well, it's the same Venn diagram. Stress, a susceptible microstructure. In our case, it's the strength of the steel, but stress corrosion cracking, do you have carbides along the grain boundaries of the stainless steel that it can etch and eat away because of the difference in composition? And do you have chlorides that are going to eat that away? So at a higher level, this at a lower level, this is hydrogen stress corrosion cracking, but we don't usually call it that. Sometimes people do. But again, hydrogen stress corrosion cracking would occur at the cathode, whereas most corrosion occurs at the anode. In any case, this is time to failure versus temperature, and this is real data points in hydrogen sulfide, and it shows that the minimum time to failure is right around 25 degrees centigrade, and lo and behold, it's just over an hour. So why do you have to get into the furnace within an hour? Well, if you keep it hot, you can wait 5 hours. If you keep it cold, you could wait 5 hours. Room temperature is where you got to be the fastest and get it in that furnace to bake it out. And I showed you the bubbling. Those of you who weren't here at the beginning of class, I showed the video that Jerry sent you a link to, and it shows hydrogen coming out of a steel weld by just dunking it in glycerin, and you can see the bubbles coming out just like the CO2 in Sprite that I showed you before. Okay, any questions on that stuff? Okay, I gave you a handout a few days ago, last week. It was a few days ago. I think it was last Thursday, a week ago. This is out of Stout and Doty's book. And let's say that someone, and I gave you the example, that I used to work with this Simpson, Gufferson, Hager firm, these were 3 MIT civil engineers back in the 1950s. They started their own company. It's now got 500 or 600 engineers, several offices around the country. Department. He's a welding engineer, and he's walking through the shop on a Monday morning, and you can tell if something's supposed to be preheated to 100 degrees or 150 degrees. You walk past it, big, several tons of steel, and it's 150 degrees. You can feel it. You can feel it in the winter. You kind of sit there, and you're like, in the winter, you got to go up there because these shops aren't heated. And in the summer, you kind of walk away from it because it can get pretty hot in these shops in the summer when you start preheating tons and tons of steel. In any case, he goes up, and he knew the procedure. He knew it was supposed to be preheated. I don't remember the temperature. And you put your hand up. If it's 200 degrees, don't put your hand on it. Okay. He put his hand on it. It was cold. And he asked the welder, he says, I thought you were supposed to preheat this. He said, oh, we did that on Friday. Okay. Oh, good. This guy obviously didn't understand the principle of preheat. But anyway. So I have to specify a preheat. I have to tell them what type of electrode, because they will probably in the field be using the stick electrode because it's so easy. Now more and more they're using gas metal arc, which is a semi-automatic process. But whatever it is, I have to tell them what types of electrodes they can use. Then it's going to tell me, do they have to do a post-weld heat treatment? And it will tell me for that steel at what temperature. Peening may be necessary. That great big thick thing, you could, I think it took them 3 days to weld that, okay? 24 hours a day, okay? To put in 400 passes, yeah. If you do too much, and that's the interesting thing about peening. A little bit of peening is good. It creates surface residual stresses, compressive stresses on the surface. If you over-peen, you're going to start getting like the peened head of a ball peen hammer that starts introducing cracks. And so over-peening can reduce fatigue strength. Under-peening will not, well, optimum peening will give you much better fatigue strength. Under-peening can give you low fatigue strength. Over-peening can give you low fatigue strength. To tell you a story on peening, this was 1969. I was between my freshman and sophomore year. I was working at the Naval Air Rework Facility in Norfolk, Virginia, rebuilding jet engines. I wasn't rebuilding them. I was an engineering intern, okay? And Vietnam War was going on, and we were getting engines back from Vietnam, and we had to, out in the shop, they had to rebuild them. Well, one of them was all ready to be shipped, all reassembled, ready to go back to Southeast Asia, and they did a final inspection, and one of the inlet fans, right there, and you're looking at the front of the engine, had a little crack in it in the titanium case. Well, to take that off, you got to disassemble half the engine and put a new case on. And they were in a hurry for these engines. And so my boss says, okay, we're going to peen it. Well, you can't shot peen in the engine because you get little steel balls all over everywhere, little BBs all over everywhere. If that gets in the engine, it'll destroy the engine, called foreign object damage. So he designed a little tool, which the shop made up. It's just a little finger that would, on a little pneumatic tool that would go bang, 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 bang. Okay, just bang, pound the surface. So I had to go out as the person from the engineering department and witness the testing of this. So I'd tell the guy, okay, bear down like you're comfortable, pushing down on this, some downward force. And he would take a little strip of steel, and it would be like 1 inch by 4 inches, and it's called an almond gauge, A-L-M-E-N. And he would peen the top surface, and then we'd measure the bow. The amount of bow tells you the amount of compressive stress you introduced in the surface. Okay? So I was there. He would peen it. I would time him. He'd try to cover the whole area. And then I would measure the bow, and it was just scatter all over the map. Okay? We couldn't get any reproducibility by and large on this peening operation. I bring the data back into the chief engineer, and I show it to him. He says, oh, okay, use these parameters and go out there on that engine and have him peen that crack. Or actually, they first had to weld the crack and then peen it to stress relieve it. You had to stress relieve this titanium. So I go out, I witness the time, the peening the guy does. Of course, it's not as simple as the almond gauge, which is nice and flat. This is a weld that's got a little hump on it, so he couldn't even peen it the same way. Nonetheless, we did it. I come back and I report, okay, we've done it. He says, sign this. I said, what's this? And he had already signed it, but he needed 2 signatures, 2 engineering signatures. He says, this is certification that we've done this repair on this. I said, well, and that it's a good repair. I said, well, what happens if I sign it? He says, if this plane goes down, you'll be in jail within 24 hours. I said, oh, okay. So I signed it. Okay. I mean, I'm signing, I have professional responsibility that we had done our best job of painting that, and we had done our best job. Whether it was any good or not, well, we don't know, but after 40 years later, 43 years later, I don't think that engine's still running. I think I probably won't go to jail for that. But part of the theme of that story is sometimes you just have to take risk, okay? But that was thin material. I didn't understand all this at that time, but my boss probably did. It's relatively thin material. The residual stresses weren't that bad. The Pratt & Whitney spec said we were supposed to do X, Y, and Z. Well, forget Pratt & Whitney. A bunch of theoretical, physicists sitting up there in Harvard. Okay, so you just do what you have to do sometimes, but you don't do it without some knowledge. Well, I did at that time. Anyway, it's a true story. I always think back on, should I have signed that? I actually have come to the conclusion, yeah, I probably should have signed it. I know enough now that I figured it was okay. Okay, so we now want to figure out, well, we've been doing tests for 70, 80 years on trying to understand stress, hydrogen, and hardness. One of the tests, we need to reproduce residual stresses. And one of the tests that people use is called the cruciform test. If you look in Stout and Doty, which was written back in the 1940s, they would take a plate, they would put another plate on top, and they would fillet weld around the edges. They'd bolt them together initially and weld the fillet weld. You bolt it together so it wouldn't bow up on you and turn into a V-shaped joint on you. So they take a high-strength bolt, bolt it together, and they weld it with their electrodes, and they then look at it and see if you get a crack. Very, very sophisticated test. Another one was the cruciform test. These are kind of like 50, 60-year-old tests, where you basically take 3 plates and you weld them together on the ends, and then you put a fillet weld here, a fillet weld here, a fillet weld on the other side. And the 4th one is the one with the highest restraint, where the plates can't move, and that's the one you look for the cracks. Okay? So you can get, with relatively small pieces that are not 2 inches thick, you can use a half-inch thick cruciform plate, and you can get yield level stresses on the type of steel you're interested with, whatever your electrode is. Okay? Pretty crude tests. Now, when I was a welding engineer at Bethlehem Steel in the mid-70s, we might use, the Japanese like to use the Tekken test. The Tekken test was nothing more, you take like a 1-inch plate or a half-inch plate, and you cut one of them in cross-section like that, the other one you bevel straight across, so you do a double bevel on one, and you do a single bevel on the other, and you put a little weld right in here. And you see if it cracks. Because the Tekken test, there's tremendous residual stress here, even though you're only using small plates. Small test, Tekken, anybody know what Tekken means in Japanese? Railroad. Okay, this was a railroad test. Japanese were building lots of railroads still in the 70s and 80s for transportation, subways and things like that. And that was the Tekken test. But there are dozens of these types of tests where you try to use a small amount of material and test the weldability of your steel, whatever its strength level is, whatever electrodes you're going to use, you do a quick test and see if you get a crack. Okay? I think I told you the other day that if I'm welding 100 KSI steel or 120 KSI steel for a bridge, if I'm welding a 70 KSI steel for a bridge, I don't really have to do much of anything. I'll show you what we have to do. 120 KSI, I have to test that steel afterwards to see if I developed any cracks. I can't just weld it to my recipe and assume everything's good. I'm going to have to go inspect it afterwards at the higher strength level. Why? Because I can use almost any electrode with this steel and it won't, you know, a little bit of care, and I won't get enough hydrogen. This one, I could get cracking, but it requires that I wait 48 hours before I do the test. Because if I tested 1 hour later, I may not have gotten a crack yet. Okay, and then I could pass it and say no cracks, and 3 hours later there would be a crack. It's delayed cracking, so far as that goes. You know, can't tell you how many times people say, "Wow, we have a crack here, but we know it wasn't hydrogen cracking because we tested it right afterwards." And I say, "Well, how soon did you test it?" "Oh, right afterwards." I said, "Well, how do you know it's not hydrogen?" "Well, we tested it. There's no crack." You know, well, it could have formed afterwards, okay? After your 1 hour that you did your, you have to wait. And the U.S. Navy waits 7 days before testing for cracks. So one of the things you do to prevent cracking is you preheat or post-heat the steel. So what I want to do now is hand out an appendix from the Structural Welding Code. Okay, we're going to spend a little bit of time on this appendix.